This video, I'm going to work in Wolfram-Cloud Mathematica, and I'm going to play with circle inversion, and I'm going to find the inverted circles of the circles inscribed in a honeycomb lattice. So I'll choose one circle from that's inscribed in the honeycomb lattice, use it as the circle of inversion, and sort of start to invert the surrounding circles. Okay, so just in general, the circle inversion, I'll call it simply circle inversion. You have this idea of you have some circle and you can map points inside to the outside and vice versa by choosing a radial line from the origin of the circle to whichever point, say in this case, the interior point P. And then you want the product of the two distances from the origin, so OP and OP prime, to be equal to the radius squared. And if the radius squared is 1, then that product is 1. Okay, so here it is. OP dot OP prime is R squared. And you can make some fancy fun pictures with lots of circles. I'm going to make something like that, but it will be different since I will be inverting a different set of circles. Okay. So first I'm going to set up a hexagonal lattice, which is going to be made of sort of hexagons, and then I'm going to have inscribed circles in them. So first I just wanted to have a single hexagon with a single circle. And in Mathematica, you're working with this graphics method. The circle method, there are different versions of the method, different signatures. But I'm going to use the signature where there's a point, an XY point for the origin, and then the radius. The hexagon it's a regular hexagon. It's a regular polygon. Here, the 6 here over here is making it a hexagon. This, just like in the circle, is sort of an origin, sort of the center of the regular polygon. And then the length parameter here is the distance from the center, the origin, to the farthest point. So it's not the closest point, which would be, then they would both have 1, but it's the distance to the farthest point is how they've defined it. In that case, this is 2 on the square root of 3. Okay, and you could just make yourself a little triangle and fit yourself that is the right distance. And then, so I have a graphic. Here is my one graphic to get the hexagon. I've used, when I'm sort of adding, in addition to what it is I'm plotting, the regular polygon, I added an edge form thick so that I was drawing the outer, some of the things default, like a circle defaults to a sort of empty, just sort of an edge, whereas the regular polygon sort of defaults to being filled in. So I had to add explicitly an edge form to have an edge, and then gave it an opacity of 0 so that there was no fill, so I could sort of see inside if I need to. Okay. So that is the graphics for the hexagon, that is the graphics for the circle, and then I say show and I put them together. Okay, so there we have that. Okay. Now I want to start to make my honeycomb. So I have a sort of a list of, it's going to be a list of graphics things, and then I'm going to sort of show them at the end. So in the beginning, I start off with an empty list. I repeat what I had above, and that is making here's the graphics for the hexagon, the center hexagon, and I add it to my list. And then I make my circle and add it to my list. And then I do a loop from 0 up to 6, not including 6. So I'm going around my hexagon. And I am making, and n is here the nearest neighbor. So these are the neighbors that touch the original hexagon. And I am making sort of the same size hexagon, 2 in the square root of 3 for the size, 6 for the number of sides. And I'm just sort of going around the circle with the proper sort of radius and having new, so this distance from here was 1, so this distance up here to this, the second center was 2, and so I'm going around a sort of circle with radius 2 and getting new sort of every 60 degrees and getting centers for my new polygons, and the same thing for the circles. And then I decided to color these circles blue. So I'm going to map these circles on, invert these circles and put them on the other one. So I will make, when I invert those circles, I will make them blue so you can remember the sort of correspondence. So here I am, I've got a loop. I am adding to my list of graphics things, and then finally I show my graphics things. And here is the beginning of my honeycomb lattice. I have my original center hexagon with an inscribed circle, and then 6 nearest neighbor hexagons. Okay, and then I want to invert these. When you do a circle inversion of an outer circle, it will become an inner circle. If anything touches the circle, that point gets mapped onto itself. So when I'm doing this circle above, it's going to become another circle. It's going to share that point above. The distance from the center up to this farthest point is going to be, remember, it's a unit circle, so 1, 2, 3. So the distance in the inverted circle is going to be, if that was 3, going to be 1/3. And so then I have a circle going from 1/3 to 1, and then the center of that circle will be in between. So I have, here I have my original circle and original hexagon, and now I'm doing the inverted ones, and they had a radius of 1/3. That's one of the features of these sort of inverted circles, is that sort of have these nice, the radii are these nice fractions. So the positions, the centers are sort of at 2/3, and the radius was 1/3, and I added them. So there are my inverted. So these circles inverted, and then it will sort of adjust the size of the image. So then so this circle is a unit circle, and this circle, this large black circle, is a unit circle. It's just the Mathematica is changing the scale of the diagram for me. Okay, so that's the first set, the nearest neighbor inverted circles. Okay, so the next thing I'm going to do is add my next nearest neighbors. So I'm going to go sort of, I don't know, along this diagonal, or sort of directly above will be a little bit farther away. So the next nearest neighbor is in this little sort of interstitial site here. And I added them and made the inscribed circle green. So again, so this, I'm going back and forth between non-inverted and inverted. So right now I'm in non-inverted. I have my original nearest neighbors, and then I'm adding my NNN, my next nearest neighbors, and I make the hexagon all still the same 2 on the square root of 3 with 6 sides. And I just have to do a little work to find the centers. So this 6 on the square root of 3 is the sort of distance, and then here are the sort of appropriate angles going around. All right. So, and then the circles are the same, and they have radius 1. So there are the next nearest neighbors in my honeycomb lattice and the inscribed circles, and I've made them green. And now I am inverting those. So one, they don't touch the circle of inversion, but they touch the previous circles when they are inverted. So that's down here. So they were sort of farther away. So when I invert them, they're going to be smaller and closer. So there they are, sort of sitting, within these crevices. So the nearest neighbor inverted are the blue, the next nearest neighbor inverted are the greens. And you just sort of, if you know that that the circle, when you invert a circle, you get a circle. And so then if you sort of work through a point or two, that's usually sufficient to give you an idea of where the new center is and what the new radius is. And so I sort of scribble that on a scrap piece of paper that I'm not showing you. I'm just showing you the result here. So here, the new thing here are the NNN. This is, but I'm doing the inverted honeycomb. And these are the next nearest neighbors in the inverted honeycomb. So I had to find the centers of those circles. And that came up to be this funny 6 square root of 3 divided by 33. But the radii, so it's a little harder work sometimes to find the center, or the center doesn't always look nice, but the radii tend to be these nice numbers. So 1/3, 1/11th, and there they are. Okay. So I'm only going to go one more layer. And so then I went for the next. So I had the blue were the nearest neighbors, these green were the next nearest neighbors, and then these purple are the next nearest neighbor. And they're just sort of farther along these sort of original directions. So directionally, they're a little easier to figure out their locations because they're just farther along. So again, this was the unit circle. So what's the point up here? There's 1, 2, 3, 4 radii from the center. And that was, and there it is. There's my 4. So there is that I'm a distance, that the center of those circles are 4, and same angles as the first set. The angles are slightly different for the next nearest neighbors, but the next nearest neighbor and the original nearest neighbor are sort of angularly the same, and this one, and they're just sort of twice as far away. And so that is that drawing. So now I want to invert the purples. Okay, so they're farther away yet. That's what we mean by next nearest neighbor, or next nearest neighbor in this case. So they're a bit farther away, so they're going to be a bit smaller. And there they are. So they're in radially, they're in the same direction as the original blue nearest neighbors. These are the purple next nearest neighbors. And you find and again, you know it's going to be a circle, and in this case, you're confident sort of about the direction, and then you just have to find the sort of radii. And so you've just find 2 points on the original circle, maybe the close one and the far one, and invert those 2 points. And so that was 1, 2, 3. So there was a 3 for the closer one, and then 1, 2, 3, 4, 5 for the farther one, and I'm inverting them, so I have thirds and fifths, and that combination of thirds and fifths, you can sort of see where these 15ths are coming from then. And so their position was 4/15, and their radial size was 1/15. And there they are. Those are these little purples sitting in. So we had the blues, the nearest neighbors, then the greens sat sort of in between, and then the purple in between those. And everything that was touching, the blues all touch the original circle, the greens touch 2 blues, and then the purples touch 2 greens and a blue. So a blue touches the original circle, a blue touches 2 greens, a purple touches 2 greens and a blue. So those relationships, those kissing, touching relationships are maintained by the inversion. Okay. Then, I don't know, just glutton for punishment than I am, I decided that I wanted to look at the inversion of the honeycomb and start to do that, not do quite as much of that. I wanted to invert the honeycomb, and the honeycomb is straight lines. Okay, so and straight lines, or straight line segments, lines are really, in some sense, circles that have an infinite radius. So it's sort of similar in that, outer circles are inverted to inner circles, outer lines are inverted into circles. So circles are inverted to circles. Lines are really just circles with a very infinite radius. And then that line, if you were to extend it, now I'm just doing a line segment, but if that line were extended, it would go to infinity, and the point that maps onto infinity, or the infinity would map onto, would be the center of the circle. So if I extended these line segments, the inverted line would be a circle that went through the origin of the circle of inversion. So that gives me a good hint in sort of where they are, that I want them to be. I need to figure out their center, but I know that they are going to, a point on the, if I continued the circle, if I drew a full inverted circle from some exterior line segment, it would pass through the origin. And then, so that helps me usually figure out the origin of that circle and the radius of that circle, and then the harder part. And some points below, I'm just more or less eyeballing it. But the harder part then is how much of the arc are you going to draw? Okay, so let me draw it and then come back and maybe talk about it a little bit. But okay, so I took, remember what I'm just inverting this sort of first set of these. So this line, first thing I am going to do are these sort of bounding lines. And they're going to be, and so there's a touching point. So the circle, when that line is inverted, it's going to become an interior circle, and that circle's got to go through the origin. So it must have a radius. It's got to touch the edge. So it must have a radius of 1/2. So these lines are also going to have sort of nice radii. And so I'm going to draw that was the inverted circle. So that was the inverted circle. This is the first inverted inversion of a hexagon line segment, and that's the one that, those are the ones that touch, and they had a radius of 1/2 that we just argued. And then the harder part is you can, in Mathematica, when you draw a circle, so I'm drawing an orange circle, and here's my origin, and the radius was 1/2, we just argued. So and then you have an angular range, a starting and ending angular range. And that was, for me, the harder part to figure out. But that gave me this. Okay, so that gave me this outer thing here. Then next I drew go back all the way up here. The next thing, so I drew these bounding lines, then I'm drawing the radial lines. Radial lines map onto radial lines. And so the next thing I have is a set of lines. So the radial lines, right now I'm mapping lines, and lines map to circles, but radial lines map to other, are circles with an infinite radius that map onto other circles with infinite radius. So they map onto lines. So here are these lines, these radial lines. And so that is these lines here. Okay. Then I jumped, just because it was easier to figure out, the far edge, the far edges, because I knew, again, they have this sort of similar direction of the first ones. So figuring out the centers are fairly easy, and because you've already done it, and you just have to sort of adjust the distance a bit. And so that was this second set of orange lines. or the third set of orange lines, and that's these little arcs here. So they are farther away, the lines are farther away, so the circles are, and you just have to imagine if you drew all these circles, this big orange circle, this little orange circle, that all those, if I drew the full circle, they'd be going through the origin. Okay, because you have to go through the origin because you are a line segment. And if I extended the line segment, it would go to infinity, and infinity maps onto the center of the circle. So, and then finally, I switched colors, these magenta ones, and they were these lines, this sort of, I don't know how to quite describe it, but they were the hard ones. Now you can see that this line is a continuation of this line. So they're different arcs of the same circle. That makes it a little bit easier. But and that is these magenta arcs down here. And so here are my magenta circles. And the radii are always nice. You know, finding the center is quasi-challenging. Finding the radii is really simple. The radii are always nice. It is the centers sometimes challenging because of the angles. And what I really found challenging, and it was just sort of in the end eyeballing, are these sort of arc lengths, or not arc lengths, but the angular arc length, where to begin and end the angles, and sort of for each circle there were sort of two arcs. And again, I'm pointing out up here that this line segment and this line segment are on the same line, so that they're on the same circle. They're just different arcs of the same circle. So they got the same center of the circle. They're aligned, so they must go through the origin. So they've got the same center, but they're just different arcs of the same circle. And that produced these. So that was these magenta ones. So this was the close side, this was the far side, these were the radial, and then these magenta ones were the ones that were sort of at an angle. And then I just threw it all together. So I just wanted to add back in my next nearest neighbors and next nearest neighbors, along with this first hexagon inverted, to sort of put it all together and show that they all the things sort of are appropriately touching. So here I have in my nearest neighbors, in my blue, I have what used to be on the outside was a hexagon, but now is a bunch of arcs touching it, and they're also touching the circles that they need to touch. All right. So that was fun. I just was jealous of these people who had these gorgeous pictures with all these circles, and I wanted to make something similar, but not quite just reproducing what they did. And this is what I came up with. All right. Thanks for your attention.